Take a look at equivalent circuits with phasors. We're going to look at addition and subtraction of phasors and understanding that it must be done in rectangular form. Multiplication and division can be done in either form, but it's simpler to do in polar form. So we're looking at using some of our mathematical manipulations that we've learned in the past in dealing with complex numbers, in this case phasors, and determining what is the easiest way to handle. Do we leave it in rectangular form or do we need to convert it to polar form? So it just depends on the operations that we're doing. Multiplication of phasors usually occurs when simplifying complex numbers in which impedances are in parallel. So in short here, when multiplying impedances, put the impedances in polar form. Magnitudes are multiplied together, angles are added algebraically. When dividing impedances, magnitudes are divided and angles are subtracted. So in finding a circuit impedance when the circuit admittance is 300 at an angle of minus 30, that should be degrees, let's put it in there, 30 degrees microsiemens. So Z, in this case the impedance, we know is equal to the inverse of 1 over Y. So Z then in this case, where the admittance, Y, is equal to 1 over 300 at an angle of minus 30 degrees in microsiemens. So Z can be handled very easily by just saying, okay, let's just move the angle out of the denominator. So we move it up, and in doing so, all we've done is change the sign. We've seen this before. Change the sign to a positive. So now we're at 1 over 300 microsiemens, and the angle is in the numerator. So we end up with 3.33, which is the reciprocal of 1 over 300. And in this case, since we have a value of microsiemens, when we do the math, we end up with kilo ohms at angles of 30 degrees. So a little more complex problem than using some of that. Two impedances, Z1 and Z2, are in parallel. Z1 is equal to 15 at an angle of 60 degrees k ohms. Z2 is 10 at an angle of minus 60 degrees k ohms. I hope you can see we're looking at setting up our problem so that we're going to have some canceling, some subtractive canceling going on here. So we want to find the total impedance. So in this relationship, notice product over the sum. We've talked about that before. Z1, Z2 product, Z1, Z2 over the sum. So we're going to simplify the denominator first. Okay, looks pretty complex here, but it's just really a stepwise process. So Z1 then in polar was given to us. To turn it into rectangular components then, R1 is equal to the magnitude, 15 k ohms, times the cosine of theta, 7.5 k ohms being our result. X sub L then, in this case, becomes 15 k ohms, the sine of theta, 13 k ohms. Now we do the same thing with Z2. That was given. We decompose our magnitudes into our rectangular form. So R2 becomes 5 k ohms. X sub C becomes minus 8.66 k ohms. So now we can put it back together as Z1 and Z2, but now in rectangular forms. So we just take all the terms we just found, 7.5 and 13, go in the first one. 5k and 8.66k go into the second one. So now we can add the two together to determine our sum of Z1 and Z2 by handling them algebraically as complex numbers. So it just becomes a sum of 7.5 by 5 gives us 12.5. 13 minus 8.6 gives us 4.33. So in doing this, we have our sum, which was the denominator, in rectangular form. So in the numerator, notice we left it in polar form. 15 at an angle of 60, 10 at an angle of minus 60, we multiply the terms together. Okay? So now let's look at converting Z1 and Z2 then into polar form. Okay, so Z1 and Z2 rectangular, we just solved for 12.5 plus 4.33. If we take the tangent of theta XL by R, we end up with 0.347. Take the inverse tangent, we get an angle of 19.1. So Z ends up being the definition of sine theta. Remember, sine theta is equal to x sub L over Z. It's the sides of the triangle, okay? Don't get confused by it. It's the sides of the triangle. 4.33 k ohms, the sine of 19.3, gives us 13.2 k ohms. That becomes our hypotenuse. So Z1 plus Z2 polar becomes 13.2 k ohms at an angle of 19.1 degrees. So now we can take this and put it back into our relationship that we started with over here. We have now combined our components together to get a polar form in the denominator. So now we have everything set up over here in polar form. So 15 by 60 times 10 by minus 60 divided by 13 by 2 at 19.1 degrees. So we multiply all of our magnitudes together, 15, 10. Notice that we set this up so that our angles are going to cancel out, like I told you. 60 minus 60 leaves us minus 19.1 in the numerator. And we end up with, because that was moved from the denominator. So we end up with that minus 19.1. Our magnitudes here become 15 times 10 k ohms at an angle of minus 19.1. The denominator has simplified to 13.2 k ohms. The phase angle remains in the numerator now as minus 19.1 k ohms and a magnitude of 11.3. Okay, so it looks like a lot, but it's just a matter of, you look at where it is you're trying to get to. We're trying to get to Z total, impedance total, and in this case, they told us to use the product over the sum. Okay, it seemed like a lot. So now, in the next section here, we're going to take a look at equivalent circuits for parallel series conversions.